Namaskara. In this session, we will continue our discussions on closest pair problem. We have already seen order n log square n algorithm. In that algorithm, we have done several clever moves to reduce the combining cost. Initially, the combining cost was order n square. Then, by avoiding lot of unnecessary comparison of or computation of the distances between the pairs in different halves, we have restricted it to delta band, points in delta band. And even within the points in the delta band, we had what is known as a delta cross 2 delta boxes, and we considered only the points in these boxes. So, for each point we had defined a delta cross 2 delta box. This will be delta and this will be 2 delta box within the band. And we have already argued that there are at most 7 points other than the given point possible in this box. You can have a maximum of 7 points other than the given point. So, we need to compute the distances only between the points which are in these boxes. You do not have to consider the points outside them, because they will define a larger distance. We do not need to compute such distances, and this has led to distance computation of order n distance computation in combining stage. Okay. However, in order to recognize these points, we have to sort the points in a delta band. This was the costly step. Everything else was order n step, whereas this one is the costlier step. So, the natural thing is, if we can get this also done in order n time, then the overall combining cost would become order n. Currently, because sorting of these points in delta band takes n log n time, we have the recurrence equation T of n is 2 times T of n by 2 plus O n log n. This cost is due to the sorting process, and that is the reason why the cost is n log square n. And now we are going to see how this can be reduced. So, there are several ways in which we are going to bring in certain efficiency and simplification, so that we have much faster and simpler algorithm. Okay. First, we will change the specification. We will also do little bit of pre-processing to avoid finding the median. Okay. Earlier, we wanted to split the point into not only two disjoint set, We want those points to be in disjoint regions. In computational geometry, it is important that we work in disjoint regions so that they are truly independent and the computation in one does not overlap with the computation in another. So, it is not simply the set of disjoint points, but those disjoint points set are physically located in disjoint regions. So, we wanted to find a median, split all the points that are less than the median and greater than the median and so on. And this is a very complicated process because finding the median algorithm, though is order n, is fairly complex. Implementing that on a large point set is again more complex. Okay. So, we are going to avoid it by simply sorting the points in the increasing order of x. So, we will use certain notation here. P is the point set, the input point set. So, you have P1, P2, Pn is the Px is the same P the same points in P, okay, in increasing order of x coordinate values. So, Px is the same set of points. So, given P you can find Px by sorting, and this can be done in n log n time. So, the complexity for getting is order n log n. Okay. From the input point set P1 to Pn, consider only x coordinate values, apply any n log n sorting algorithm, you rearrange the point set and the resulting array of points, you call it as Px. So, you are going to call this as Px 1, Px 2, like this you can call them as Px n as the n points. Okay, these are the their x coordinate values, you call it as x1, x2 symbolically. If you denote, then these are in the increasing order of x values. Okay. The reason why we do this Px is, if you consider m equal floor n by 2 and consider x m, this acts as the median which we have done earlier. Less than or equal to xm, but all these x values are smaller and other things are larger. So, naturally xm acts as a splitting point which puts the point in two different regions. Therefore, here SL or the points on the left are simply the point Px1 to Pxm, and points in the right, the set of points in the right is Px m plus 1, the other points Px n. Very simple, okay, because it is a sorted array, it automatically arranges the elements, and the first half will be in one region and the second half will be in a region to the right of it, they are in disjoint region. Therefore, by a very simple sorting and choosing like this and defining SL and SR, we simply solve the dividing phase in a nice way. Now we have disjoint set of points in disjoint regions. Okay. So that's the advantage of pre-sorting and then considering this. And we are going to do the following. We will output Py. What is Py? Py is P in decreasing order of y coordinate values. P is in the decreasing order of y. This is Py. This is a name given. It's the same P. Consider that presented in the decreasing order of y value. And this also I want in addition to delta. This is my main goal. Now more for less. So our closest point algorithm, closest pair algorithm takes P, rather takes Px as input and it outputs Py and delta. That is the set of all points rearranged in the increasing y order and the closest pair distance delta. So I want more. Now you see that we can achieve this in much less time. Okay. So let's look at the same algorithm, the steps. First you split into two parts. Okay, with respect to Px, Sl and Sy are, you don't have to do anything to construct Sl and Sy. Px is split into two halves at M. Px is an array. You can split Px array into two parts and that's the input. You can, in fact, we will not, because we assume that Px is the input. All right. So let's clear this off. We will assume Px is the input. The output is, that is, input is set of points sorted in x value. All right. So first recursive call, closest pair Px 1 to M. So this is going to output Py 1 to M and delta L, because it is the first half. Cp Px M plus 1 to N. This is going to output the same set of points in decreasing order, M plus 1 to N and delta R. Okay. So there is a set of points in the decreasing order of y. There is another set of points in the decreasing order of y. So Py 1 to M, Py M plus 1 to N, they are available. Now what we are going to do is merge Py 1 to M and Py M plus 1 to N to obtain Py 1 to N. Okay. So now you have the set of all points sorted in y order is available in Py. And what you want is the set of all points in the delta band, the set of all points in the delta band sorted in y order, descending y order. So how do you get? It's very simple to get that from Py, right? Py is set of all, what is the delta? Delta is minimum of delta L and delta R, and delta band is, this is xm, this is xm plus delta, and this is. So, what are the points in the band, delta band? B is set of points in delta band, and the points in the delta band is defined as the set of all points P such that, or Pi, I was using capital, sorry. All points Pi such that x m minus delta less than or equal to xi is less than or equal to xm plus delta. So, what I do is I want B in the sorted Y order. So, we do this scan Py, for each point Pi belongs to Py, retain only for each point retain Pi if xm minus delta less than or equal to xi, its x coordinate less than or equal to xm plus delta. Otherwise, ignore. For each point in retain Pi if this, otherwise, okay, else delete it or else ignore it. Since B is constructed from Py, since B is constructed from Py, the y coordinate values are automatically sorted in the same order as Py. You are constructing from Py. Therefore, B will also have the same property. From Py, you are knocking some points and you got B. So, if Py is sorted according to y value, B will also be sorted in y value. In other words, we have constructed a sorted version of B in order n time. Okay? You are scanning P of y and remove the ones which are not in the band by this check. Thereby, the shorter list, which is B, and B is automatically sorted in. Now, we can apply the same steps since we have the points of B available in sorted Y order. The previous algorithm, the steps we used in the previous algorithm can be used, and now all steps have become order n. Okay, that is the because we have already asked for more, and the more has helped us in reducing the combining cost. Okay. So, let us summarize our discussion in the following pseudocode. This is a crucial step, which is earlier we have spent n log n time for this. Earlier we have constructed B. After constructing B, we sorted it out, and that took n log n time. But the sorted version of B can be obtained in linear time because we have sorted version of the points in y coordinate values is already available for us in the more for less model. Okay. So, closest pair Px, okay, it outputs Py and delta. Comment, Px is set of points P in increasing x coordinate order. Delta is closest pair distance. Py is set of points in P in decreasing order of y coordinate values. Okay. These are the comments. Now we can straight away start, and P is a set of n. Okay. N points. This is a set of n input points. So, if n equal to 1 or n equal to 2, solve the problem trivially or directly. For example, if there is n equal to 1, there is nothing like closest pair, delta is 0, and then there is nothing you have to worry. If there are 2 points, that is only closest pair, there is only one pair, and whatever is its distance, that is the delta, and those pair you output in increasing y order, that is all. So, this is solved trivially if n else m equal to floor n by 2, okay, m equal to floor n by 2. Now, you apply closest pair on P x 1 dot dot m. This is the set of points sorted in x order. So, let it give P y 1 dot dot m and delta L and C P x m plus 1 dot dot n. This gives P y m plus 1 dot dot n and delta R. The first thing that you compute now is let delta equal to minimum of delta L and delta R. Now you merge P y 1 dot dot m and P y m plus 1 n to obtain P y 1 to n. this is the merge step, and okay, let B equal to set of all points in Py, right, the set of all Pi belong to Py such that its x coordinate value is in the range delta, okay. So, x m minus delta less than or equal to x I less than or equal to x m plus delta. Let B equal to Pa belong to. So, comment B is constructed my goodness, B is constructed by scanning Py and retaining only the points that satisfy the bounds defining the band B. So, each point you check this condition, and if it satisfies, you retain it, otherwise you ignore it. So, you are going to generate, therefore hence B is sorted by y coordinate values. It inherits the order, okay. So, let B, so let us assume we will also introduce another notation for defining let B be P1, P2, etc. Pk. Let us assume that this is the k points in B are, these are the k points. Now, delta C equal to infinity for I equals 1 to k, for j equal to I plus 1 to I plus 7, delta C equal to minimum of delta C and the distance between Pi and Pj so thereby delta C is the minimum distance between the points in the delta band, okay. By the time the loop is completed, for each point the distance would have been computed with all other relevant 7 points, and thereby the minimum would have been found out. So, by the time these two for loops finish, all right, so you would have got delta C. Notice that the complexity of this loop, there are two loops, the complex, even if it is n, is less than or equal to 7n, because here you are per point you are only computing at most 7 distances. Therefore, 7n is the complexity of this. Now, what is delta? Delta is minimum of delta L, delta R and delta crossing across the line. You consider the points and then now you return Py and delta. Now, the recursive calls will also return Py for the points it has considered. That is the reason why you had here Py of these two 1. Okay. So, you can see that this is the complexity is Tn by 2 recursive call. This another complexity Tn by 2. This is order 1. Merging is order n. You have 2 sorted sequence and you have done the merging. And you are constructing B by looking into this, and the construction is order n, because you scan Py, put either a point in B or not, and when you are putting the points in that order, it is automatically sorted. Since the sorted version of points in B is available, I do this. We have already seen that this is 7n order n. Therefore, the complexity is T of n is 2 times T of n by 2 plus order n, and that is order n log n. Notice that we started with Px, but computing Px is another n log n. Okay? P to Px is another order n log n. So, this is the pre-processing cost. From Px, getting this is order n log n, and overall the complexity is order n log n. So, you can see how more for less is helpful. What was causing a more complex step in the conquering phase, we made it more efficient by returning more by the recursive calls. So, the recursive calls has output the sorted y values. Therefore, constructing sorted B becomes easier or order n. Okay. Therefore, you can see that the more for less is such a powerful idea that it is leading to very efficient algorithms. Okay. The same divide and conquer idea can be made lot more efficient, and that is the major advantage here. So, let me summarize. Okay. Let me summarize the various things that we have discussed in the divide and conquer idea. The divide and conquer paradigm is a very clever paradigm. It is one of the best ideas along the algorithmic thinking, and the analysis of divide and conquer algorithm, the exact analysis is mathematically really challenging. The first case study that we have used in merge sort we looked into the mathematical aspects. We have seen the details of, first we have seen how to deal with the floor and seal exactly, then how to prove the bound by constructive induction by using induction for all bounds for all n. Getting the bounds for all n can be done by computing recurrence equation for special values of n and use monotonicity. So, we computed T of n equals T of floor n by 2 plus T of seal n by 2 plus n minus 1 for n of the form 2 power k special values and then used monotonicity. To prove the bound T of n is O n log n for all n. This is proving the bound only for special values. You are extending it for all n. So, we have seen certain mathematical details related to merge sort. Okay. And then we were looking at the ways in which the naive divide and conquer algorithm can be improved. How to improve direct divide and conquer solutions. One thing we can do is that we can look for whether bottoming out earlier is helpful. You do not have to go on splitting to the smallest problem size, even slightly larger size. If you can bottom out, it contributes for efficiency. We have seen that the recursion tree becomes smaller when we attempt to bottom out at larger subproblems. So, that is one opportunity to improve. The second one is split. How do you split? Should you always split equally, floor n by 2, seal n by 2? Not necessarily. There may be several other ways in which when you split, it could be advantageous for you. So, you should explore the possibility of splitting wisely. These are two important ways in which you can see whether a divide and conquer algorithm can be improved. The next one is, can we divide into several subproblems, more than 2, not necessarily 2. These are all the tips for working with dividing the problem into 2 subproblems. Karstuba's algorithm tells you how to handle with dividing it into more than 2 subproblems. Karstuba algorithm gave us a very interesting way in which to divide the problem into several subproblems, and then by reducing the number of such subproblems, we can gain efficiency. How to divide and more number of subproblems. That is more than 2. In that, how do we bring in efficiency? So, this we have done using master theorem. We have taken help from master theorem, and we have seen some patterns from the master theorem is helping us. They are guiding us in identifying the number of subproblems that we may have to use to bring in efficiency. We have learnt a lot of things of that kind through Karstuba's algorithm. Then we have seen an unusual way of improving the divide and conquer algorithms, that is more for less. So, in more for less, we have seen that a direct way of designing a divide and conquer algorithm has certain complexity, but when we try to add something more as a part of the output, it contributes for efficiency in the combining cost as well as in the overall cost. That's what we have seen in several case studies: maximum subarray sum problem, dominance count problem, and inversion count problems, okay, and then the closest pair problem. In all of this, we are seeing that changing the specification of the problem to give more is helping in arriving at more efficient solution. Okay. With this, we conclude our discussions on divide and conquer algorithms. Thank you.